If we know the theory of adhesion, then we understand that we need to apply a surface treatment to the substrate. That's what we are going to see in Module 3, surface treatments. We know from the theory of adhesion that we need to apply a surface treatment if we want to have a good adhesion. So it's time now to look at the recipes that exist in terms of surface treatments for the different materials that we want to bond. But let's first talk about the importance of the surface treatment. We already have analyzed a joint in the introduction as a series of links. And the purpose of the surface treatment is to make sure that this link and this link are never the weakest link. It's possible to prove that the work of adhesion is higher than the work of cohesion. So, in theory, this should never happen. This should never be the weakest link. If it is, that means that the surface treatment is not the most appropriate. So, that's really the importance of the surface treatment, to make sure that it fails either in the adherent or in the adhesive, never here at the interface. It's important, surface treatment, for immediate strength, for tomorrow, for 1 week, but even more for the long-term strength. And this is what it is illustrated in this slide. You have the joint strength of aluminum single-up joints as a function of the time immersed in water for different types of surface treatments, from very, very simple up to very, very sophisticated. And you can see that at the beginning there is a difference, but not that much. It's with time that a fancy, elaborated surface treatment gives you much more than a simple surface treatment. In other words, you need a sophisticated surface treatment if you want to have durability, if you want to have a joint that will withstand load in 10 or 20 years. Surface treatment is particularly important for that, for durability. Which characteristics affect adhesion? When, of course, you have the contamination. The surface normally that we are going to bond are oily, mold release agent, grease, dust, etc. All these substances have a low surface energy, and you know that this decreases adhesion. But you can also have weak boundary layers. Basically, we are talking about oxides that are weakly attached to the base material, like for example rust in steel. And this line here, we are talking about a very weak adhesion. And you might have a strong adhesion between the adhesive and the oxide, but because the oxide is weakly attached to the base material, it will fail here at this interface with a low load. So really you need to remove this weak boundary layer and create a stronger oxide that will withstand the load and will not provoke an interfacial failure. What are the general principles associated to surface treatments? You may have 1, 2, or 3, depending on the complexity of the surface treatment. You might have material removal. For example, if you apply a solvent, you remove the dirt. You might have surface topography. If you apply emery paper, you change the roughness of the surface. And you might also have chemical modification of the surface if, for example, you apply a plasma treatment in a polymer. You might have the 3, or you might have only 1. It depends on the complexity of the treatment. If you want something really elaborate for a joint that will be durable, in general, you have the 3, all right? Then you can classify the treatments or the processes in passive treatments and active treatments. Here, like the name explains, you don't have any chemical change at the surface of the substrate. So basically, you just clean or you change the topography. That's it. That's what you obtain, for example, if you apply emery paper, or if you apply shot blasting, you apply particles at high speed on the surface that leave the surface highly irregular. Something like this. You see, this is aluminium substrate. Here it was not treated. Here it was shot blasted, and you can see clearly the change of topography, but there is no change of chemistry, all right? Then you have the active processes, where you have really a chemical transformation at the surface. In the case of the metals, we are looking for the formation of a well-defined oxide or structure. In the case of polymers, we are looking at the formation of polar groups. You remember the polar forces which are stronger than the dispersive forces, and this can be obtained with several types of physical treatments like corona discharge, flame, or plasma treatment. Really, the active process is when we want something that is strong and that is durable, okay? Let's give an example for the metals of an active process that would be acid etching or anodization. It's the same, but with anodization, it's more controlled. And what we are left with at the end of the process, of the treatment, is this surface, very bright. And at the surface, if you observe with scanning electron microscopy, you observe this very porous oxide, very strong, very resistant to corrosion, very firmly attached to the base, and porous. And you have here a scheme of how this looks. You see all these pores here, firmly attached. And this is excellent because the adhesive will penetrate here in these pores and will, in addition to create van der Waals forces, will also create interlocking, mechanical theory of adhesion. So that's really, really nice. If you want, you can have a better idea here. Again, it's a substrate not treated, and here treated chemically with anodization. You see, it's much brighter, all right? Okay. Another example now for active, but this time using physical treatments. You have three main physical treatments: corona discharge, flame, plasma. They are used specially for plastics to increase the surface energy. In the case of plasma, what do? You apply plasma, we are talking about ionized gas, you bombard the surface. This will break the molecules that are at the surface. These molecules will react with oxygen and create polar bonds, and this increases the surface energy and the van der Waals forces that the adhesive will make with the substrate. So you have examples for materials that are typically used in the aeronautical industry, aluminum, composite. There are many recipes for these materials. We know now with this module, with this session, which treatments we should apply to guarantee a strong bond, and more than that, a durable bond.